Hello there, everyone. Welcome, warm welcome. Thank you for being here. Grab yourself a notebook, a pencil, or pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we have a Calculus BC problem from 1995 AP Calculus BC exam. The reason why I'm not using Desmos on this one, even though I do have the tab open, is because we don't really require it here, and if you're given Desmos, this question would almost be too easy to be on the calculator portion. So while it while it still may be digital for the free response question, it's going to be presented digitally, kind of how you're looking at it now, and you're just going to be working on your papers. So these are actually decent simulation of what you're going to experience on the non-calculator section, because you are going to have to turn in your work and you get points based on your work. You guys know the drill for that. Okay, well, as usual, give yourself about 12 minutes, 15 if you really need it, to do this Taylor series related problem. So you're going to have to recall something about Taylor series, and then when you're ready, you can join back and see how we did it here. All right. Let's get started. F is going to be a function that has derivatives of all orders, so we can take as many derivatives as we need. And they don't give us an equation. We're going to have to write a polynomial that represents the equation. That's the Taylor polynomial. So for part A, it says to write the second degree Taylor polynomial for f. That is very important that it's for f. And it's about the point x equals 1, so this is like our A value, you might call it, and use it to approximate f of 0.7. Now people get confused because there are two x values here. They're like, which one do I use and where do I use it? This one is used, A equals 1 is used for the Taylor polynomial construction. So to create the function itself, you're using that A. It's about the point A equals 1. Now this is the x value that we're going to eventually plug in to the model. But first we have to create the model. That's why it says use it to approximate. Okay, just making sure that's really clear. Now second degree Taylor polynomial, I might just call it T2. We're going to have it be, and it's centered at A, we're going to have it be f of A plus f prime of A, that's one order higher, times x minus A to 1 power. And it's like over 1 factorial, but we don't really have to write that, I guess. Plus the next derivative, f double prime of A times x minus A to a higher power now. And this is divided by 2 factorial, which happens to just be 2. So I'm not going to put the exclamation point. Okay, so we just have to use the information they gave us, the assumptions that we're allowed to use here. It tells us a lot of the information about the derivatives at x equals 1. So that means we're going to write it as, let's see, this is just going to be 3 plus, yeah, I should probably put minus because we have because we have the derivative here as -2, so minus 2x minus 1 plus the second derivative, which we have right here, that's positive 2, times x minus 1 squared, and then that's over 2, so this is going to cancel nicely. Let's go ahead and plug in 0.7. Oh, so we can say f of 0.7 is approximately, because f of x is approximately this Taylor polynomial. Okay, good. So we have 3 minus 2 times 0.7 minus 1, that's going to be a negative. So we're going to have negative 0.3. And then also in this parentheses, we're going to have negative 0.3 squared over 2, so I'll cancel those now. All right, pretty straightforward. 3 plus 0.6 plus 0.09. So we get 3.69. That is our approximation. Pretty straightforward, yeah? Now, let's do part B, which has us go one step further. It's the third degree Taylor polynomial for f about the same point, and use it to approximate f of 1.2. So now we're going to extend this a little bit. We're going to use the same information pretty much, but now we're going to have, I'll write it really quickly. Let's copy and paste this. Come here, you. Now we're going to have that f of x is approximated by the third degree Taylor polynomial, or approximately, yeah, squigglies. Squigglies for approximations. And we need another term. We need f triple prime and x minus a to the third. And this is going to be over 3 factorial, which is 6. Okay, that means that we can approximate f of 1.2 is approximately this third degree Taylor polynomial of 1.2, which is, what is that going to be? So we have 3 minus 2 times 1.2 minus 1, that's going to be 0.2. So all of these x minus a's are going to factor like that. 0.2 squared over 2. And then what was f triple prime? I didn't check that one yet. That's 4. Okay. You might notice that I'm not going back and forth to like check all of these things. I'm using my memory, guys. You have to use your memory when you're solving problems. Like, keep track of what you're doing and what you just did in part A. Like, don't get so tunnel visioned that you don't realize that you did some stuff in the past. And, you know, if you have to keep going back and forth and checking, that's spending time that you just don't need to use. Once you see these, you know, you can double check them once in a while. I'm not saying you have to have a perfect memory, but like, save yourself some time. Use your memory. If you don't have a good memory, strengthen it a little bit. Because like that, wouldn't that help you? Speaking of which, so then what was f triple prime? Did you catch it? Or did you forget already? It's 4. 0.2 cubed over 2. Okay, so let's just evaluate. This is pretty simple. We can cancel this and this. And similarly, we can cancel that and that. So we're going to have 3 minus 0.4 plus point, careful, it's not just 0.4. I know you just saw the 0.4 and want to call it 0.4. It's 0.04. And then we have plus 0.0. It would be 0.008 times 2. We'll just call that 0.0160. Okay, so definitely do not let a couple of decimal numbers be the reason why you get this wrong. If this is on a non-calculator section, you have to be careful. 2.656. That is the approximate value. Beauty of Taylor polynomials. We don't even need to know what the function is. If it had an equation to begin with, we can just approximate an equation. It's like so awesome. Okay. Part C. Write the second degree Taylor polynomial. Wait, didn't we just do that? Nope. For f prime. The derivative of f. They even said that. Very nice of them to clarify that. About the point x equals 1. So this is the a again. But it's not going to be the exact same equation. And use it to approximate f prime of 1.2. Now, here's the thing. It could be tempting to say, oh, I know how to go from f to f prime. You take a derivative. And if I take a derivative of a third degree, I'll get a second degree. However, you should not simply take a derivative of all of these terms and then use that as f prime's approximation. I'll give you this. It would be like, it wouldn't be super far off. It's not the worst thing to do, but that's not what they're asking. Like, it would be a decent approximation, but it's better to just do what it is that they're asking. So we're going to take we're going to take the pattern of a Taylor polynomial, and we're going to basically elevate each of the terms. So instead of starting with f of a, we're starting with f prime of a. I might as well just put the 1 in there, honestly. Plus f double prime is like the f prime term because it's 1 degree up, or I should say 1 derivative order up. F double prime of 1 still times x minus a, so times x minus 1 over 1 factorial, which I don't really have to write. And then we're going to have f triple prime at 1. This is like the typical double prime term. I don't know why that was such a tongue twister for me. Double prime term. Say that 3 times fast. Double prime term, double prime term, double prime term. Okay, we're awake now. So I could plug these things in, by the way. You remember what these are? Again, want to try to use your memory, guys. X minus 1 plus, yeah, you remember now, 4, right? Good. 4 over the 2, I'm just going to call that plus 2. X minus 1 squared. This is the approximation. And you don't really need to work it all out because we're just going to plug something into it. We're using this model to approximate f prime of 1.2. We're going to say that it's approximately t2 of 1.2. Did I plug it in there? Yeah, I did plug it in there. And I did plug it in there. Okay, good. Just making sure that I wrote that that's what I'm using. I'm using this x value in the Taylor polynomial. And the fact that this is t2, and I also called this t2 later, that's probably not the best in terms of like very strict math etiquette, but I don't think it's going to penalize you if you just sort of label this as like part C. It should be fine. Because then it's very clear, like, hey, I'm just talking about the stuff in part C. Okay. A little intermediate blab there. So if we're plugging in 1.2, these again are just going to be 0.2. Man, these birds are singing in the void. Hear those birds in the background? So this is going to be 0.4, and this is going to be 0.04 times 2, so 0.08, for a total of 2.48. Beautiful. I really don't want you guys to be scared of Taylor series problems because it's very likely that if you're in BC, you're going to get one of these types on the exam. Now, you might not have to do Taylor polynomials for every single part of a free response question. You might get a free response question that uses like 1 or 2 parts that involve Maclaurin or Taylor series. But I just want to have you prepared for how to set this up. And if you don't know the pattern for the Taylor polynomials, make sure you're familiar with that. Get yourself familiar with how to set that up and how it works with the denominators. They'll usually only have you go to like a 2nd or 3rd degree Taylor polynomial, unless it's a really easy derivative to take like sine or cosine. There are some general power series that you should be familiar with, but maybe we'll save that for a power series problem in another time. All right, that's enough of the blab out of me today, guys. Hope you learned something. Really appreciate you were here, and we will see you next time in the